Okay, so we been talking about last time balancing equations. We also been talking about some types of reactions last time. A couple reminders that when you balance equation, obviously the only thing that we do change are the coefficients, which are the numbers in front. We never change any of the subscripts or anything like that. When you're all done, you do want to make sure that obviously it is balanced, but all the coefficients do need to be whole numbers. They do also need to be the simplest set of whole numbers when you balance an equation. We saw a couple examples where obviously you can use a fraction, which sometimes is kind of an easier way to solve a problem to balance it. But you do need to clear the fraction when it's all said and done, so you can't leave it as a fraction or anything like that. We also saw that when balancing equations that contain a number of sort of polyatomic ions, again, as we talked about, it's sometimes a lot easier just to kind of keep those guys together and balance them as whole units rather than going element by element. We then kind of started talking about ways to classify reactions. And again, there are really three reasons, three sort of driving forces for why reactions take place. And again, the first one is the transfer of electrons. The second reason really a reaction takes place is the formation of a solid or precipitate. And the third reason really is sort of the formation of water. You pretty much could boil down all chemical reactions to pretty much those three things. Either somewhere electrons being transferred, a solid's being formed, or water's being made. And those are really sort of the reasons why chemical reactions sort of take place. We started focusing in on last time really on sort of the solid being formed. And in terms of classifications of reactions, as you may be familiar with, and as we saw a little bit yesterday, and we'll see a little bit more today, there are sort of multiple ways that you could classify as same reaction, depending on sort of what you're looking at. But overall, there's really kind of two big categories of reactions that take place. One that we started talking about last time is double displacement reactions. And double displacement reactions is really sort of like I sometimes will say, kind of the big umbrella for which a more specific classification can happen. Double displacement reactions pretty much always have this sort of setup that occurs. And the way you could recognize them as double displacement reaction is there are two ionic compounds. So you should have two things that really are ionic, a positive and negative guy. And pretty much 100% of the time, it is always just the positive guys that will basically switch partners. And what they will do is they will form new ionic compounds on the other side. And in certain cases, as we talked about last time, maybe one of these guys make a solid. And again, that would be what is referred to more specifically as a precipitation reaction. Or one of these guys may make water. And usually water being made is a result of an acid-base reaction that occurs. So under the big umbrella of sort of double displacement reactions, we do find these couple of really more specific types of ways of classifying reactions as either precipitation reactions or acid-base reactions. The other big sort of category of reactions which we should get into today are redox reactions, and that's sort of the other big category of reactions that we'll talk about. And underneath redox reactions is a lot of different ways to classify a number of reactions kind of more specifically. So all reactions pretty much boil down to those three things: water being made, solid, or electrons being transferred. And all reactions almost boil down to those two big categories of either they fall under double displacement reactions or they fall under redox reactions. A couple other things that we talked about last time was also the idea of electrolytes. Electrolytes, again, are substances that basically when they go for a swim there will break apart into ions. It is the presence of those ions which help conduct electricity. So we have strong electrolytes. And if something is a strong electrolyte, pretty much it will 100% break apart into ions, which means in that solution, there is absolutely none of the whole unit still together. It has completely broken apart into ions. And that's why it's considered a strong electrolyte. It produces really a solution that has a lot of positive and negative guys swimming around. It's going to help conduct electricity really, really well. And we saw a picture like a light bulb, for example. And again, that light bulb would go on very, very brightly because it's conducting electricity really, really well. There are certain things that are weak electrolytes, and weak electrolytes, on the other hand, really do not break apart all that much. They do break apart a little bit, but they do mainly stay together. And remember, the weak electrolytes typically have the arrows that head sort of in both directions. And that indicates, again, that it is a reversible reaction where, again, heading towards the product side is the forward direction. Heading towards the reactant side there is the reverse direction. And basically what happens in a case where you do have a weak electrolyte is mainly what you have floating around in the solution is actually the whole unit still together. But it is able to produce a little bit of ions as it breaks apart. And because it's able to produce a little bit of ions, it's still able to conduct electricity, but nowhere near a strong electrolyte. So again, in terms of the light bulb example, the light bulb will still come on, but it would be very, very dim. So it really, it's still able to conduct electricity. And then we also have things that are non-electrolytes, and these are really molecular sort of compounds where even though they may be able to dissolve in something like water, they will not produce any ions. So because they don't produce any ions, they will not be able to conduct electricity at all. And obviously the light bulb will not go off. A lot of places where we see sort of strong electrolytes, which 100% break apart, are a lot of strong acids, strong bases, and a lot of ionic compounds are pretty much strong electrolytes. A lot of weak electrolytes are a lot of weak acids and weak bases. Those kind of make up a lot of the weak electrolytes that we do see. We also talked about solubility and the idea of, how do we know if we kind of put together a couple of ions, will we expect to get something that's going to make a solid or something that's not going to make a solid? And if something is soluble, in terms of sort of equations and writing equations, which we sort of did talk about 3 different types of equations. So we had something like this one I think we looked at last time, silver nitrate, plus a little sodium chloride. Again, this is a double displacement reaction, positive, negative, positive, negative. Again, these two guys are going to switch partners. And that makes something like silver chloride and a little sodium nitrate. And we could use solubility rules to help us determine, are these things going to be soluble or insoluble? We could use solubility rules. For example, on this first one, it contains nitrate, as we talked about, which is pretty much soluble in everything. So as soon as you see something with nitrate in it, it will get the aqueous symbol. And the aqueous symbol, again, is really a solution. It's something that will mix well and soluble in each other. We look at something like sodium chloride, sodium, which is group 1, they're soluble in everything, so there's no exception. So once again, as soon as you see that, you also know it's going to get the aqueous symbol next to it. When we look at something like silver chloride, chlorides, bromides, iodides, they are soluble in everything, but they do have a few exceptions, and 3 exceptions that they have is silver, lead 2, and mercury 1. And in this case, because the chloride is actually hooked up with silver, instead of being soluble like it normally should be, it will actually be the opposite of that and become insoluble in that case. And we would actually get this guy being a solid. So anything that is insoluble based off of those solubility rules should get the solid sort of notation next to it. And once again, on this last one here, we have sodium and we have nitrate. And really, you can look at either one in that case. They are both soluble in everything, and they would all get the aqueous symbol sort of next to it. This, as we talked about last time, is what is referred to obviously as the molecular equation. And when we do have the molecular equation in a situation like this, we can write an equation that really describes what is going on, say in the beaker or wherever you have these solutions together. Because silver nitrate is an ionic compound, it's going to be really a strong electrolyte, which means really when it's in that sort of beaker, if you will, it will 100% break apart into a silver ion and a nitrate ion. Same thing with the sodium chloride. It's a strong electrolyte, so you have none of the sodium chloride units still together. You basically have sodium ions and chloride ions floating around in that solution. When we get to something like silver chloride, which is a solid, the reason it's a solid is because they are obviously together and they stay together. They don't break apart. So we do keep that guy together. And a reminder that when you're writing this type of equation here, anything that is a solid, a liquid, a gas, or a weak electrolyte should actually stay together. You shouldn't break it apart when you get to this equation. The sodium nitrate is also a strong electrolyte, which means it will break apart into sodium and again nitrate here. This is what is sometimes referred to as the total ionic equation, or again, some people call it the complete ionic equation. And it basically describes what's happening in that solution. We basically got all these ions floating around. Some of the ions come together to make silver chloride and drop out as like a solid, and the other ions are still floating around in the solution like the sodium and the nitrate. We can find on this equation what are referred to as our spectator ions, and those are again the ions that are exactly the same on both sides of the arrow here. And in this case, it is the sodium and the nitrate. And spectator ions, much like the name implies, they're just kind of hanging out. They're not really making the actual product of this reaction. So we do cancel them out on both sides. And as we talked about last time, if you do it correctly, they should really completely cancel out. If you find yourself that they don't completely cancel out, you either have a wrong sort of formula or you did not balance the equation correctly. And what you're left with is the last type of equation we talked about, which means it is basically in this reaction, the silver ions floating around are going to find the chloride ions, and they're going to make silver chloride, which is the solid. And this is what is referred to as a net ionic equation. And again, it is really the bottom line of what is happening in this reaction. It is basically those silver ions and chloride ions coming together to make the solid, making of a solid, again, one of the reasons why this reaction takes place, because we are making that solid. Any questions on any of that stuff we talked about last time there? Okay. All right, then let's try a couple more here. Why don't you try this one? Why don't we write the molecular equation, total ionic equation, net ionic equation for this reaction here. See what you come up with. So let's do all three of those. Balance. Okay, let's take a look and see how you're doing. So as we also talked about last time, it's really important when you're writing equations, especially if you're given things in words or you're trying to predict what's on their side, again, that you sort of get all the right formulas down first and then worry about the balancing. Again, you don't want to do both of those things at once. So here we're doing the reaction, precipitation reaction. So we do know there's going to be a solid, obviously, that's going to be formed. Between potassium carbonate. So remember, potassium is a +1, carbonate is a -2. So when we put that together, we get K2CO3. And it's going to react with nickel 2 chloride. So nickel Roman numeral 2 means this guy's got a +2 charge. Chloride is -1. So that's going to be a NiCl2. At this point, if you're not sure what type of reaction, you can look at both of these things, hopefully, and understand that it is a double displacement reaction, as we got a positive guy, negative, negative guy. So on the other side of the equation, our positive guy is going to switch partners. So this guy's going to end up with the chloride. This guy is going to end up with the negative guy. Once again, here, when we do it on the other side, we want to make sure we get the correct formula first. So although there's a 2 next to that potassium there, it is just K plus and Cl minus, which means the proper formula is KCl, not K2Cl2 or anything like that. So you want to make sure you get the right one down. And then our nickel, which once again has a +2 charge. Our carbonate here has a -2 charge, so that would give us something like NiCO3. Any question on how to get all the guys there? Now you can hopefully see I was not concerned at all on the right-hand side there with the balancing aspect of it. I got all the right formulas. Now I could go and balance it. And obviously I need to lay up a 2 there, I think. And that's about it, I think. So now we do have the balanced equation at this point. We also might want to include our states using our solubility rules. Frankly, in the first one, as soon as I see potassium, I know that guy is going to be aqueous because potassium is soluble in everything. When I look at the chloride in the second guy, it is soluble in everything except for silver, lead, and mercury, which obviously nickel is not any of those exceptions, so it would also still be aqueous. When I come to the other side, I know that I do have a solid that's going to be formed. So I do know when I look at the first one, I have potassium, so I'm pretty much done there. And by process of elimination, if you did not have the solubility rules available to you, could not remember it, the only one left to be a solid at this point would obviously be our carbonate. Any questions on any of that there? So obviously what we have here would now be our balanced molecular equation. We can now write our total ionic equation. We would break apart our first guy, the 2 potassium. The 2 would actually again come to the front there, and we would have 2 potassium ions plus 1 carbonate ion as that first guy breaks apart. Our nickel 2 chloride would also break apart again into a nickel with a +2 charge. And the 2 for the Cl will come to the front in this equation and tell us we basically have 2 chloride ions floating around, also aqueous here. Coming to the other side, we would have 2 potassium ions and also 2 chloride ions, as that 2 in front would be distributed to everybody behind it. And lastly here, our solid would stay together because, again, it is a solid. This would be our total ionic equation. Any questions on that one there? Now we can use our total ionic equation here to identify our spectator ions, and it looks like we got a couple of potassiums on both sides, which is good. And we also got a couple of chlorides on both sides. So those would be our spectator ions, leaving us our total our net ionic equation of it is the nickel coming together with the carbonate, forming our nickel 2 carbonate in this case, would be our net ionic equation. Any questions on any of that there? So again, a couple of things here in this problem sort of reinforce some of the stuff we talked about last time. Make sure proper formulas, then balance. Don't try to do them together. Again, breaking apart into our total ionic equation and our net ionic equation. Any questions on any of that? That's the same one, I think. All right, a couple more here. Predict the products and balance the equations. And why don't we do all 3 of those again? You could do the total, the net. So looking at the first one here, once again, positive, negative guy, ionic compound there. So we do know we're going to get a double displacement reaction. So the potassium will go with the nitrate. So once again, potassium is +1, nitrate is -1. So that's going to give us a KNO3. The silver, which is +1, will then end up with the chloride, which is -1, which will give us silver chloride in this case. We can balance it up, but I think we are balanced at this point. We got 1 potassium on both sides, 1 nitrate, a silver on both sides, and a chloride on both sides, so we're good. We can use our solubility rules here to help predict what's going on here. So once we see potassium in that first one, that's pretty much as far as we need to go. We could also look at the nitrate, which is soluble in everything. Here we have silver chloride, as we saw before and previously. Once again, chloride is soluble in everything except for silver, lead, and mercury, which obviously would then turn that into a solid. So we would get a solid precipitate in this reaction. Again, it is a double displacement reaction. More specifically here, it is a precipitation reaction as we made a solid. If we were going into our total ionic equation, we would break apart the potassium chloride into potassium and chloride ions. We would also break apart the silver nitrate into a silver ion and a nitrate ion. We would break apart the potassium nitrate into its ions. And here we would keep, again, our solid together. And that would be our total ionic equation at this point. Once again, we can identify our spectator ions, which is a potassium and a, not chloride, it is a nitrate, actually. Oops. So potassium and nitrate being the same on both sides there, which would be our spectator ion. Once again, if we cancel those guys out, will leave us our net ionic equation, which in this case is, again, the silver coming together with the chloride to form our silver chloride in this case. Any questions on any of those three equations there? All right, looking at the bottom one, once again, we do see hopefully the formula here of a positive and negative guy and a positive negative guy. So once again, double displacement reaction happening. Our sodium will hook up with our chloride here. Once again, not going to look at the little subscripts there. Sodium is +1, chloride is -1, giving me, again, the proper formula of NaCl. Once again, not Na2Cl2 or something like that. Going to move our calcium, which is +2, to our sulfide, which is -2. And that's going to give us a little calcium sulfide that looks like that. At this point, we can balance it, and it looks like a 2 right about there should do it. We will use our solubility rules here to help us out. So sodium, pretty much all I need to see on that first one, and I know it's going to be aqueous. Now, what about calcium sulfides? So sulfides are typically insoluble, but one of the exceptions to sulfide actually is calcium. So if we take a look back at our solubility table there that we saw yesterday, it's here somewhere. There it is. So once again, sulfides are typically solids, but calcium is one of the exceptions here, which means in this case, that guy will actually be soluble. So when we do make our calcium sulfide in that case, this guy also is going to be aqueous because of that. Any questions on that there? So what does that mean? That means that if we were to write our total ionic equation, we would get a couple of sodium ions in this case. We would get a sulfide ion, as that would break apart. We would get a calcium ion, and we would get a couple chloride ions from our calcium chloride. We would get a couple of sodium ions, a couple of chloride ions, and I'll just go underneath here. We would also get a calcium ion and a sulfide ion. That means that my spectator ions are everything, right? Everything would cancel out. So did I have a reaction in this case? I did not. There's actually no reaction in this case. Yeah. Remember, in order really to have a reaction, you need electrons to be transferred, you need a solid to be formed, or you need water to be formed. In this case, you basically just got everybody swimming around happy. Now everybody's coming together. Everybody's just swimming around in the beaker as ions basically floating around in that solution. You wouldn't see any type of solid form. So like one of your wells, when you put the two solutions together and just look the same, nothing formed, that's basically what's going on. Any questions on that there? Any questions on total ionic equations, net ionic equations, molecular equations, how to predict double displacement reactions? Okay. All right. We'll do one more here. We'll just do the molecular equation on this one. It's fine. So just write the balanced molecular. Okay, let's take a look. So here we got some ammonium sulfate, and it is aqueous, and a little lead 2 acetate, also aqueous. And once again, this is a positive, negative guy, positive, negative guy. So classic double displacement. We're just going to switch partners. A lot going on here, but we do just want to take the basic units of these guys. So that basic unit is ammonium, and this basic unit is sulfate. Basic unit of this guy is lead with a +2 charge, and acetate with a -1 charge. So again, when we put these together, we want to make sure we put them together properly here. That would then give me actually NH4C2H3O2. And I'll go underneath, and our lead and our sulfate coming together. Again, once I have the proper formulas down, then I can balance it. And in this case, it looks like I need a 2 right about there to do so. Any questions on that? So again, very, very common error people make is they try to incorporate all these extra 2s and stuff into the actual formulas. We can use our solubility rules looking at our ammonium acetate. Ammonium is soluble in everything. There's no exception. So that should be aqueous. Also, acetate is pretty much soluble as well. Lead 2 sulfate. Sulfate going to be insoluble here with lead, and we would get a precipitate in this particular case. Any questions on that there? Okay. So there's our pictures of what's going on. Now, we've talked a little bit here about obviously precipitation reactions, but really the other sort of place where we do see really double displacement reactions happening is in acid-base reactions that take place. When we take a strong acid or a strong base together, we typically will get 2 things to form. We will get what is referred to as a salt and water. And water pretty much comes from the acid, which is the H+, and the base, which is the OH-, is basically coming together to make water. A salt is just an ionic compound. So it's just an ionic compound that comes from the 2 really spectator ions that are hanging out in that solution. An acid is really a solution that, as we talked about, has the ability to form H+ ions in solution. It is also sometimes referred to as hydronium ions, which is H3O+. When we talk about acid and bases, H+ pretty much and H3O+, which is the hydronium ions, are essentially equal to each other. They both fairly represent the acid part of the solution. So if you go on to 200B, you'll talk all about acids and stuff like that. But they're pretty much the same thing as the acid in the solution. A base is something that, again, is able to produce hydroxide ions in solution, and that is your definition. And when we talk about producing hydroxide ions, or we're talking about producing H+ ions in solution, we're talking about producing them freely in solution, so they're by themselves floating around freely in the solution, and that's what makes something, an acid or a base. So like our hydrochloric acid, which is a strong electrolyte, will break apart into H+ and Cl- in solution. 100% these guys. Again, is that formation of that free H+ that's floating around, which basically makes it a acid and a strong acid because it's 100% of that. How do you get H3O+? You could write this exact same reaction I did here where the HCl reacts with water, basically. And when you do that, you will get H3O+ and Cl-, and then they're equivalent to each other, that H3O+, In this particular case, what's going to happen is this guy's going to send an H plus over to water, and that's going to make H3O plus. So that's why H plus, H3O plus are pretty much equivalent to each other. They basically represent an acid in solution, and really you get H3O plus if you include water in the reaction, which a lot of times people don't, and when you do an acid-base reactions, but that's why they're equivalent to each other. So an acid-base reaction will result in water, and as we talked about earlier, that is, again, one of the three reasons why a reaction takes place. So again, this is really the main thing that happens when you do an acid and base together. Here's a table of some of those strong acids that we talked about, I think, last time, and some weaker acids as well, which might help you with, electrolytes and stuff like that. But perchloric acid, nitric acid, sulfuric acid, hydrochloric acid, and also you could add HBr and HI. These are also strong acids. Here's some of the weaker acids down here. So acetic acid, as we talked about last time, hydrofluoric acid, carbonic acid, and those guys are weak acids. So again, all these strong acids will 100% break apart into ions in solution. These weak guys will pretty much stay together. So again, I would say weak acids are very common weak electrolytes that you come across. So if you get to that total ionic equation, you would keep those guys together and not break it apart into ions in that particular case. Here's some strong bases and some weak bases. And once again, pretty much like I think I said the other day, if you go kind of where lithium and sodium is on the periodic table, down to potassium, and then hang over this way to calcium and so forth. All those guys with hydroxide in the formula are typically strong bases. Kind of your group 1 and group 2 on the periodic table typically will make a lot of the strong bases that you see. Some of these are some of the weak bases here, and I would say this guy is probably the most common one that you come across, and that's ammonium hydroxide, which is really in most cases referred to as just ammonia, and H3 is a very common weak base. So kind of the same idea. Obviously, if you had something that's sodium hydroxide, potassium hydroxide, you would 100% break it apart. If you were dealing with something obviously like ammonia or something like that, it wouldn't break apart or anything like that. It would stay together. So acid-base reactions are sometimes also called acid-base neutralization reactions, and they are also, again, really under the double displacement umbrella. And that is because when we look at something like this reaction here, which is hydrochloric acid plus sodium hydroxide, we consider it kind of like two ionic compounds. This is a positive negative guy. This is a positive negative guy. So same thing is going to happen here. Our H plus and our OH minus going to come together, and our sodium and our chloride here will come together. Once again, it is always pretty much in this strong acid, strong base situation. It is always the H plus from the acid, the OH minus from the base that is going to produce the water in this reaction. So you basically can, if you want the salt part, which is the ionic compound, kind of just put your hand over those parts and those things, and what's left over will produce the salt. And the salt would come from the sodium ion in this case, hooking up there with the chloride ion to make our salt in this case. So it is still that double displacement reaction. This again is the salt, and obviously that is water. And most of the time the salt is going to be soluble. You could potentially get an insoluble salt, but I would say probably most of the time it will be soluble. And we would make water, which is a liquid, obviously, here. And this would be obviously our balanced molecular equation. We can write our total ionic equation for this guy. And because hydrochloric acid is a strong acid, it would break apart into H plus and Cl minus. Because sodium hydroxide is a strong base, it also would break apart into sodium ion and hydroxide ion. The salt on the other side is just an ionic compound, so it will break apart into that. and water, which is a pure liquid, will stay together. So we would keep the water together in this particular case. When we look on both sides here, we could find our spectator ions, which in this case is the chloride and also the sodium. And if we cross those spectator ions out, we are left with our net ionic equation, which is, once again, the H plus from the acid is going to find the hydroxide from the base, and they're going to form our good friend H2O, which is water. And again, the reason why this reaction is taking place. That is the net ionic equation. Frankly, for any combination you like of strong acid and strong base that you put together, if you go through it for any combination of those two things, that is pretty much where you will end up. H plus and OH minus will make water in that situation. So we can see that again if we pick two different sort of acid and bases. If we took something like nitric acid, for example, and potassium hydroxide, which again is a strong acid, strong base, so positive, negative, positive, negative. Once again, these two guys are going to come together, and the potassium and the nitrate's going to come together. When those H plus and OH minus come together, that is going to give us our water, our potassium, which is +1, and our nitrate, which is -1, going to give us our potassium nitrate. And once again, that would be our balanced molecular equation going through our total ionic equation here, H plus and NO3 minus, as it will break apart, K plus and OH minus, as that guy will break apart. Water will stay together because it's a liquid, and our K plus and our NO3 minus will break apart. Looking at our spectator ions again, in this case, we do see it is nitrate on both sides and potassium on both sides. Canceling them out once again gives us the exact same net ionic equation. And that is fundamentally what is going on in this reaction, H plus OH minus coming together to make water. So once again, that is always what you're going to kind of get when you get down to it as well. If you did like sulfuric acid and sodium hydroxide, you just end up with 2 H pluses and no H minuses, which would reduce down to 1 across the board. So it'll all come back down to that. So under double displacement reactions, we have really our precipitation reactions, which obviously are guys that form a solid. And we have underneath that big umbrella of double displacement reaction, our acid-base neutralization reaction, which forms water. And really our double displacement reactions are basically responsible for those two of those three things, either making a solid or basically forming water. Any questions on that there? Now, if you did have, say, something like a weak acid involved, for example, let's say we took something like acetic acid here, which we'll do this here. And we reacted it with sodium hydroxide. Once again, this is this is actually positive, negative, and positive, negative in that case. And we're going to get our switching of our positive guys. So this guy and this guy actually is going to go this way. And what we will get in this case is, once again, we will get some sodium acetate. And we will get our water being formed in this case. So once again, we're still making water in this case. And if we did go through our total ionic equation, it would look a little bit different. And it would look a little bit different because this acid is a weak acid, which means it's a weak electrolyte, which means when we get to our total ionic equation, we would actually not break that guy apart. So we would keep it together. So we would actually keep this guy together because it is a weak acid or weak electrolyte. We would break apart the sodium hydroxide here into a sodium ion and a hydroxide ion. On the other side, this is our salt, by the way, and obviously this is our water. So the salt, which is just an ionic compound, will break apart. So it will break apart into a sodium ion and an acetate ion. And obviously our water here would stay together. So our total ionic equation will look a little bit different because we do have that kind of weak electrolyte involved there. We could still look for our spectator ions, but in this particular case, what is our spectator ions here? Yeah, it is just the sodium in this case. It is the only ion that is the same on both sides. Because that acetic acid stayed together, we don't get sort of another spectator ion happening. So really in this case, it would just be the sodium, and that would be the only thing that would cancel out. And that would leave us, again, a little bit different looking, maybe net ionic equation, which would be our acetic acid plus our hydroxide here, making our acetate and our water. This would be our net ionic. That would be our total ionic. Any questions on that? So again, that's sort of how you handle any type of weak electrolyte. You want to keep it together. It will stay together, and it will find itself in the overall net ionic equation. Because really, if you kind of take the beaker view of what's going on, in a sense, you do have this guy still together flowing around because it's a weak electrolyte, and you got that hydroxide ion happening there. And then you also obviously have your acetate floating around and your water being formed as well. Unlike a precipitation reaction, you can't really see this happening. So, sometimes you may mix these together and you're observing it, for example, and you can't really see water being formed, right? Unlike a solid where you could actually see something floating around and stuff like that. So that's something to keep in mind, especially if you're doing some type of experiment where you're mixing these two together. It may look to you like, nothing happened, but the formation of water is actually occurring in that particular case. You just visually may not be able to maybe see it actually occur. Any questions on that? So that's what we talked about there. Now, sometimes in double displacement reactions, it actually results in gases being formed. So, we talked about sort of water being formed. We talked about sort of solids being formed. Another result of some double displacement reactions is actually generating some type of gas as an end product. Now, sometimes the gas is actually generated sort of directly as a result of the ions basically swapping around and switching. And sometimes the gas is formed as a result of a sort of secondary reaction that occurs with one of the products. So in the first case there, we got some potassium sulfide and some sulfuric acid. When we put it together, we get some potassium sulfate and some hydrogen sulfide gas. So just by doing the direct sort of double displacement reaction that would occur here between the positive negative guy, positive negative, the potassium and the sulfate and the hydrogen and the sulfide coming together, we do generate this hydrogen sulfide gas. Now, in this case, when we would go to, for example, a sort of net ionic equation or total ionic equation, we obviously would keep the H2S together as it is a gas. It wouldn't break apart or anything like that. Now, if we took something kind of similar-ish, we take some potassium sulfite, which is a positive and negative guy, and our sulfuric acid, which is also positive, negative. Again, the potassium, the sulfate will come together, the hydrogen and the sulfite will come together. It will actually produce potassium sulfate and sulfurous acid, which is this guy right here. Now, in this case, we didn't directly produce a gas, but something like sulfurous acid will actually then go through a secondary reaction itself. It actually will go through what is referred to as a decomposition reaction. Decomposition reaction is where you start with one thing and breaks apart into a couple of other things. It basically decomposes. So very rapidly, the sulfurous acid will decompose into water and our SO2 gas, which is sort of what we're seeing down here. And that obviously is the generation of a gas. So sometimes these double displacement reactions can directly produce a gas. Other cases, it can sort of produce something that will go through a decomposition reaction and further sort of produce a gas. And a very common one is when something, for example, like carbonic acid is produced. Something like carbonic acid is produced, it very quickly breaks apart into water and a little CO2 gas is a very common one that happens there. Whenever you take an acid and anything that involves carbonate, like sodium carbonate, hydrogen carbonate, like baking soda on like acid, basically, right? It starts to bubble and fizz and all that kind of stuff. And that is the production of the CO2 gas that's happening there. You know, kind of like when you make the volcano, right, as well. Have you ever done that, right? And you kind of do put those things together. And, you know, that's what you're kind of seeing is that generation of that CO2 gas bringing everything up. So here's a nice little table that kind of helps you figure out some of the gas producing ones. As we saw, if you basically have a metal with sulfide, you will produce directly some hydrogen sulfide gas, as what we saw in our example there. If you have a metal with carbonate, like sodium carbonate or sodium hydrogen carbonate, and you react it with an acid, once again, as I just wrote there on the last slide, you will produce carbonic acid, which will go through a decomposition reaction and produce CO2. That was the other one that we just saw there on the slide. Anything that involves sulfite or hydrogen sulfite will basically, when it reacted with an acid, will produce SO2. And anything with ammonia here, ammonium hydroxide, will produce ammonia. That's basically what is happening with ammonia in sort of water. It produces NH3. Sometimes if you take 200B, when they ask you to go grab ammonia off the shelf, it's sometimes just on the bottle of ammonium hydroxide, sort of the ammonia in a aqueous form. But once it kind of gets into the air and react with water, it will produce ammonia gas, basically, as a result of that. Any questions on any of that there? All right, so that concludes sort of our double displacement conversation here. Again, acid-base reaction, precipitation reactions, more specific classification of those. We're now going to turn basically to all the other types of reactions, and pretty much all the other types of reactions fall under what are referred to as redox reactions. And redox reactions are oxidation-reduction reactions. And oxidation has several meanings, but the meaning that we come across the most here is basically something that will lose electrons. So oxidation is something that will lose electrons. Reduction is something that will gain electrons. Sometimes people remember this with the Leo the lion goes grr, right? Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig, right? Oxidizing is losing, reducing is gaining, whichever one you like there. So those are two basic definitions of oxidation and reduction. And it also is really the third reason why a reaction takes place, which is transfer of electrons. So all these reactions involve basically transfer of electrons. And as we will see, the redox sort of classification, once again, is sort of the big umbrella for which you can more specifically classify different types of reactions. Things like we'll see like synthesis, combination, decomposition reactions, and so forth. They're all basically redox reactions that are taking place. So for example, here we could look at this reaction of magnesium with oxygen, and maybe you did it in a previous lab or something like that, or class. Sometimes they let you take magnesium ribbon, put it in a Bunsen burner, and it gets very, very bright. And they go like, hey, observe what's happening, but don't look at it. So you don't like lose your eyesight because it's very, very bright. But what's happening here is the magnesium metal by itself has no charge. So anything with that is uncombined has I'll say no charge, but it really has what is referred to as a zero oxidation state. Oxidation state is sort of what the charge would be, and it's zero. It will lose some electrons, and as we know, magnesium will make a +2 charge, which means it will actually lose a couple of electrons, and that is what we see here, magnesium with +2 charge and some electrons coming off. Because each magnesium loses 2 electrons and there's 2 magnesiums here, that is why we have 4 electrons basically coming off on the product side, 2 for each of the magnesiums basically that lost it. This is what is referred to as the oxidation half reaction. The oxidation half reaction basically displays the oxidation part of the reaction. It displays the guy losing electrons. How do we know it's an oxidation half reaction? Well, frankly, the electrons are on the product side. Yeah, so electrons should always be on the product side. In an oxidation half reaction, like they're being lost, like they're being given off. Reduction, on the other hand, is basically somebody gaining electrons. And when we look at O2 by itself uncombined, it also has a zero oxidation state. It has no charge or anything associated with it. It's going to pick up those 4 electrons that magnesium gave off, and it's going to then get something obviously that has a -2 charge on this side. And this is what is referred to as the reduction half reaction. It is basically describing the guy that is gaining the electrons. We know it is a reduction half reaction because frankly, the electrons are on the reactant side, like they are being gained by the oxygen when we do that. If we add both of these half reactions together, they're basically half reaction because they are half of what is going on. When you add them together, you get the equation below it. And by the way, when you add both of these together, there's a couple of things that you want to make sure of before you add them together. First off is the number of electrons should always be the same in both half reactions. And that is because if there is an oxidation occurring, there will definitely be a reduction occurring. So they always occur together. And there's always sort of the equal transfer of those electrons. So however many electrons are given off by the guy losing it should be the exact same number of electrons by the guy gaining it. So it's that transfer of electrons, which again is why this reaction is taking place in this particular case. So when we add these together, the electrons should always be the same, and they also should always be on opposite sides of the arrow. If you ever have 2 half reactions where you have the electrons on the same side of the arrow, you frankly did it wrong. Yes, they should never ever be on the same side of the arrow. They should always be on opposite sides. When we add these together, everybody on the left-hand side of the arrow stays on the left-hand side. Everybody on the right-hand side of the arrow stays on the right-hand side of the arrow, and that's what we see here. These are all the guys on the left-hand side of the arrow. These are all the guys on the right-hand side of the arrow. You could think of the arrow like an equal sign in math. Yeah, you could subtract things to the other side. So we have electrons on both sides, and they should completely cancel out, like subtracting 4 electrons to the opposite side. And what you're left with is the overall reaction that is taking place, which is basically the magnesium that started with a zero oxidation state and the oxygen that started with a zero oxidation state will come together to make magnesium oxide here that has a +2 charge for the magnesium, a -2 charge for the oxygen. Any questions on that there? So if we look at this, by the way, for example, our overall reaction, we could look at it, which was the magnesium plus the oxygen makes our magnesium oxide here. And this is 0, 0, +2, and -2. Sometimes people have a hard time figuring out, what is being oxidized, what is being reduced. And you do need to be able to kind of do that to help you out here as you go through redox reactions. So there's a very simple way that you can sort of figure it out, what is being oxidized, what is being reduced. You could just use a basic number line, right? Usually to the right of 0 is positive numbers, to the left of 0 is negative numbers. And when we think about the definitions of oxidation and reduction, this guy is losing electrons, this one is gaining electrons. So if something goes through oxidation, it will lose electrons. And if somebody loses electrons, will you become more positive or more negative? If you lose electrons, you will actually become more positive, right? Because you got more protons than electrons, so you'll become more of a positive charge. So if you follow the oxidation number and you find yourself moving in this direction, in the more positive direction, that guy is going through oxidation. If you gain electrons, you now have more electrons than protons, right? And you become more negatively charged. So if you find yourself on this number line kind of moving in this direction, you are definitely going through reduction. So again, just to demonstrate how that works, if we take the magnesium, for example, we take this guy. It starts at 0. And on the right-hand side, it ends up at +2, which means it is moving in this direction. And again, that means that this guy is going through oxidation. If we look at the oxygen, which is this guy, oxygen is starting at 0 and ending at -2, which means it is moving in that direction, which means this guy is going through reduction. So it's a very sort of convenient way, just easily just follow the oxidation state and you can see which way you're going. If you're becoming more positive, you're going through oxidation. If you're becoming more negative, you're going through reduction. Any questions on that there? By the way, we already should know, for example, in this situation, magnesium is a metal, right? Oxygen is a non-metal. And the one that typically should lose electrons is always the metal, right? Again, based on those periodic trends we talked about, right? They're going to give away their electrons pretty easily. Non-metals are going to really accept electrons. So really, when you kind of have this situation of metal and the non-metal together, it's fairly simple. It should pretty much be the metal that should be oxidized always, and it should be the non-metal that will be reduced. But you will come across things where you may have two metals involved, or maybe, and you might have to sort of figure out what is going on in terms of that. Now, there's also another couple of things that go with sort of oxidation and reduction. So what we're talking about right now is talking about what is being oxidized and what is being reduced. There's also what is referred to as the oxidizing agent and the reducing agent, and those are a couple of different things. So there's something that is known as the oxidizing agent and the reducing agent. Now, the oxidizing agent is the substance that gets reduced, and the reducing agent is the substance that gets oxidized. So when you're talked about the agents, it is really the opposite of the name. So the oxidizing agent is the guy that gets reduced. The reason for that is in order for it to be reduced itself, it has to gain electrons, which means it has to cause somebody else to lose their electrons. So it's causing the oxidation in the other substance, and vice versa. The reducing agent is the guy that gets oxidized. So if he gets oxidized, he's going to lose electrons, which means somebody will then have to gain those electrons and be reduced. So when we talk about the oxidizing agent and the reducing agent, it is different than being asked what is being oxidized and what is being reduced. So you want to make sure you keep those two things straight. So in our example up here, the reducing agent would be which one? What thing would be the reducing agent up there? It would be the magnesium. So the reducing agent here would be the magnesium, because that is the thing being oxidized. And the oxygen here would be the oxidizing agent in this case. When you're asked what is the oxidizing agent, what is the reducing agent, it is always a reactant. So it always should be the guys on the reactant side that you are talking about when you're asking that. It should not be the guys on the product side. It should be guys on the reactant side when you're trying to do that. Any questions on that there? very commonplace that we see redox reactions occur, and you'll make some of these in 200B. If you take 200B, is electrochemistry. So galvanic cells, kind of like batteries as well, you know, are basically like redox reactions that are occurring. So what happens, for example, in this situation here is we have zinc that's going to kind of come off into the solution, and copper sort of come on and get plated. But in this sort of situation, anything that is sort of a solid here is our guys that are by themselves, like a zinc would be by itself, has no charge. Anything that gets a charge or gains a charge, like zinc would gain a positive charge, that would find itself in the actual solution part here. So in the actual solution part is the ions floating around, and the solids are always sort of the solid electrodes in that particular example. So here is zinc plus some copper 2 sulfate, making our zinc sulfate and our solid copper. And in this case, this is a redox reaction that is occurring. This, by the way, is also a single replacement reaction, which is another way you can classify this. How do I know this? Because zinc by itself is 0, and this is pretty much what we saw in the previous slide, the picture. This is copper 2 sulfate, which means the copper here has a +2 charge. The sulfate is -2. The zinc sulfate is +2, and the sulfate here is -2, and the copper by itself has no charge or no oxidation state. What is being oxidized here? Take a second. What is being oxidized? What is being reduced? What is the oxidizing agent, and what is the reducing agent? So take a minute or two, see if you come up with what all those things are. Okay, let's take a look. So again, if you're not sure, we can follow the oxidation states up there on top. Again, you can make your little number line if you like to help you out. Let's start with the zinc. So our zinc here is going from 0 to really +2 in this case. So it's going from 0 to +2, which would mean in that direction is actually becoming more positive. It is the zinc that is going through oxidation in this case. Yeah. Now let's take a look at, say, the copper in this case. The copper here is starting at +2, which would be like over here. And it is ending at 0, which means it is moving in this direction more negative, which means it is being reduced, right? So our copper here is going through reduction. Any questions on that there? Now, that would mean that in this particular case, our zinc would be the reducing agent as it is going through oxidation. And our copper with a +2 charge on the left-hand side would actually be the oxidizing agent as it is going through reduction. Is there anything happening with the sulfate here? The answer is no. It is -2 on the left-hand side. It's also -2 on the right-hand side. Nothing is happening with that. First off, any questions on how to identify all that? To further see this, we could actually take this equation here and actually write a net ionic equation like we did with the double displacement reactions. And we would do something very similar. We would take the zinc, which is a solid, so obviously it would stay together. The copper 2 sulfate would break apart into ions. We would get these two ions off of it. The zinc sulfate would also break apart into ions. And the copper, which is by itself in a solid, obviously would stay together. As we just talked about, the zinc really didn't change from left to right, and we see that because the sulfate didn't change from left to right. The sulfate is actually our spectator ion in this case, right? It's the same on both sides. So it's actually our spectator ion, which means if we got down to our net ionic equation to really describe what is happening here, it would be our solid zinc plus our copper with our +2 charge going to our zinc with a +2 charge and our copper with no charge here. And that would be our net ionic equation of what's going on. And if we really get more specific, the zinc is being oxidized, which means basically it is the zinc that's going to become zinc with a +2 charge and give away a couple of electrons, which would be our oxidation half reaction. And our copper 2 will pick up those 2 electrons and make solid copper on the other side here, which would be our reduction half reaction. So you could actually, for this type of reaction, write sort of a net ionic equation. And again, you can see here the sulfate really is just our spectator ion. Nothing's really happening with it. It is really what's happening here. It is the exchange of electrons or transfer of electrons from the zinc to the copper 2, which again goes back to the driving force for a chemical reaction, which is that transfer of electrons is really what's ultimately happening in this particular reaction. Any questions on that there? All right, we will lay it up there for today. I believe we're actually doing a physical experiment today, so a little double displacement reactions I think is on tap for today. So